take those sets from A naught which are covering E and consider their length actually. So what would be their length? The length is going to be I equal to 1 to infinity with respect to this L of AIs. And now since you can have many coverings actually, okay, since you can have many coverings for E, then give this measure, the measure of E, the value which is the smallest of all. Okay? Smallest of all. And it's pretty much intuitive. Think about it. If I have a set, okay, something like that, I can have many coverings for it. You know? I can have many coverings for it actually. So like this is one covering, this is maybe another covering, and so on and so forth. Okay? And now among all these coverings you want to say that, okay, which of the covering is giving you a better approximation for, you know, the abstract set that you have actually. Okay? Or which is kind of a closer to the notion of
For AIs, you don't have any restriction, like they can be disjoint.
They can be anything.
So this definition is confusing.
No, that's not confusing. I'm not using the length of the AIs actually. I'm using this side. So this side makes sense actually.
So like if I have the interval -1 to 1, and I can write it as a union of -1 over n to 1 over n. So
Let me give you something. Why we haven't put a restriction of, you know, because that is redundant actually. Think about it. So if I have a cover of E in which the sets are not necessarily disjoint, out of this cover I can create a cover, okay, which is going to be disjoint, and their length is can give their length, you know, in this sense. In other words, So in other words, if I have lots of sets which are intersecting with, you know, each other, I can break down this set, lots of sets and their union to you know, disjoint parts actually. So it's not a big deal. So in other words, when I am saying that E is contained in AIs, I can break down these AIs into disjoint parts in such a way that when I compute the length of this, it's going to be equal to the length of those disjoint parts actually, and hence you can get the sum.
here we also do the same in the other.
You know, another explanation could be, the simplest one, is that I'm not using this identity. I'm saying that, okay, since all of these AIs from A and L of AI naught, what do you call, exist, okay, then this sum exists actually. So it's not necessarily finite, it could be infinite as well. Okay, I'm not saying that this series is always convergent. Okay, so it could be divergent.
I don't have problem with this definition,
Okay.
but with that identity, like how left hand side and right hand side would be equal.
No. So this is my definition, and I have a right to define the things the way I want actually. So this is my definition actually. That I have an abstract algebra and a map L with these two properties.
Okay.
So this is my definition actually. So if I have, so this all theorem would work if you have an algebra and some notion of length associated with that algebra actually. Okay, which satisfies these two properties. Are you getting the point? If you have this, then you can, you know, construct an outer measure, enhance a measure actually. Okay, and in our particular case, our usual notion of length has these two both properties actually.
But the second one would not be satisfied. Like the same example.
Why not?
Like if I am taking x equals to r and I am taking the set -1 to 1 and writing it in the union of -1 over n, 1 over
Okay.
n. How would this
So
definition?
if you can show me, okay, if you can write, so what should I write? Okay, so what should I take?
X equals to r.
So let's take x equal to r.
E is equals to equals to minus 1 to 1.
E is equal
So let's take E equal to minus 1 to 1 closed, including or excluding?
Open different.
Okay, open. So, okay,
Okay, and we can write it as a union of minus 1 over n to 1 over n, where n belongs to natural number.
I equal to 1 to infinity, 1 over minus 1 over I and 1 over I. Would that be the case? Are you sure that you're going to get?
Yes, sir. Equal.
Okay. Alright, and then what we are saying?
Then applying that identity here. So,
So you have a 2 here,
hmm.
okay? And what did you get on this side? So you get 2 plus. By the way, are you going to have this equality? In the first place?
ये covering नहीं है, I guess.
You know, because if you take I equal to 1, you already have this interval actually.
Yes, sir.
Yes,
Open
But
or
if you are
close.
putting I equal to 2 also inside in it, so you have more than, but you're going to have a subset of this actually.
But
Yes,
we
sir.
can write this as this union of these sets. So we have already said that these sets must not be disjoint. So here the set.
Are these disjoint?
No, sir.
They are not disjoint. Then. This is what this is. So it doesn't satisfy. So in other words, in order to apply or verify this identity, you need to write minus 1 to 1 as disjoint subsets actually. So since these are not disjoint, so this will not be satisfied.
So this means here the assumption of disjoint is necessary.
Yes, it is.
Definition.
It is. They all are disjoint. In other words, if you have disjoint parts from algebra, countable disjoint parts from algebra. So didn't I said it when I think I said it.
Yes, sir. Yes, sir.
I said it.
They are
But
disjoint.
I didn't wrote it, but I said it actually. Okay. But I should have written it. Okay. It's
No.
fine.
Okay.
And I said it actually. I'm pretty much sure.
Sir, say.
अब ये कुछ और ना.
Sir,
Yes, sir. Hate through the
if you can just
I
make me clear on this, sir. Sir, by this definition of Mayer, the a circle and a unit circle and a unit square are same, sir. By this definition of
By this definition of
Mayer,
unit circle and
unit square.
what do you mean by unit circle? Are you talking from the point of view of the parameter?
Sir, if we take x to be r square, then and we take g the open set to be a circle, unit circle, then how we are going to calculate its Mayer?
Okay, so that means you're not going to allow me to. So what would be the two-dimensional version of it? So if you are taking x to be R2,
Yes, sir.
then the length of the interval a comma b, which is not now one interval, okay, but it is the cross product of two intervals actually. So a cross a1 b1 cross a2 b2. So this is an abstract notation for this interval. Would be equal to, so I'm defining it to be the product I equal to 1 to 2 of bi minus ai. Okay, so this will be my definition then.
Okay.
And then I'll have something similar for the abstract union sets. You can show that if you have an abstract open set, okay, in R2 or maybe in Rn, then you can write it as the union of such D boxes actually. So there's a term used, either you call it a cell or a D box or whatever you call it. Okay. So then you have on 2 dimensions you're going to have this kind of a notion of length. So this is only true in R. Okay. So this is what that you are saying then. If you have a bunch of things, abstract things, no matter what things you have, could be intervals, could be anything else, and a map which behaves like length, okay, or common sense length, then out of such kind of a map you can create an outer measure. And when you restrict this outer measure onto a suitable subset of, power set of x, then you can get a measure. This is what essentially you like to do. Okay? So are we happy with this definition?
So there is no difference between this definition and this definition, sir.
Which definition?
M of E, sir. The definition that you wrote in the starting of this.
We will say that this would be a particular case of this actually.
Okay.
This is abstract.
Okay.
So I'm saying it again and again that A naught is an algebra on any set x actually.
Okay, sir.
On any set x. Are you getting the point? But it's not necessarily that you should have a topology on this set x.
Okay, sir.
Since you are talking about R here, so you have this open set and whatever. Okay, so if you have a bunch of things with you, okay, defined through a set, and the way to measure the length, okay. So length is just an intuitive word. So don't treat that length as it. So length could be volume, length could be anything actually.
It's a mere.
It's a measure actually. It's some kind of, it's not really a measure in technical sense,
Yes, sir.
but just in non-technical sense, it's a measure actually. Yeah, then using such a length, you can define an outer measure, which can give rise to what we call measure. So are we happy with this definition? Pretty much natural, the way it should be. So it's like as per our expectation, nothing is strange. Then, okay, and this is true for all E subsets of X. Then you can prove actually, number one, that mu star is an outer measure. Mu star is an outer measure. The second is that so this is a kind of a measure which agrees with our intuition actually. In other words, if you compute, so if you take an A from A naught, then this mu star, and if you measure this A through mu star, what do you think what you should get actually? Because think about it. On A naught you have this notion of length. Okay? Then mu star of A should give you the length of A actually. So in other words, I am kind of extending this notion of length to the whole power set of X, but it meets with our particular cases as well actually, so it meets with our expectation. Okay, it's not something that gives you something different for the length of it. Okay. Okay. The third thing part is that every A from A naught is mu star measurable. What does it mean? I'll write in a minute. So this is third part. And the fourth is that if L is sigma finite, then there exists a unique extension, okay, unique extension to sigma of A naught of t. Okay? So there are few new terms, I'm going to define them, and then we can get into some of these things. So what we are saying essentially, so here's a bigger picture. If you have a notion of, if you have A naught, an algebra, and some notion of length on it, okay, then you can always find an outer measure which is defined on all subsets of X. An outer measure is not a measure, this is what an important thing. And then if you restrict essentially this outer measure, L is good, and if you restrict this outer measure onto the sigma algebra generated by this algebra, sigma algebra generated by this algebra, then U star is the measure itself. Okay? So this is what that, this is telling us. What does second property is telling us? Is self-evident. But self-evident means, okay, it's pretty easy to make sense. What the third is telling us? The third is telling us that, okay, it's not, so in other words, all elements in A naught are mu star measurable, and what is the meaning of being mu star measurable? Let me write it as well. Write it here. That is a set, okay, a subset of X is called mu star measurable under mu star if okay, this has been defined for so a subset of X is mu star measurable if mu star of any subset of E can be written as the mu star of A intersection E plus mu star of A intersection or A complement intersection. This is what the meaning of mu star measurability is. In other words, a set A is mu star measurable. Okay, so I must write here for all subsets P of X. If this identity is true for all subsets P of X for fixed A. In other words, no matter what E you take, you can always think about it. So what does A intersection E mean actually? So if I want to interpret this identity, what would be the interpretation of this? How can I interpret it? So in other words, if you want to, if you compute the outer measure of A with an arbitrary subset of, with inside E,
Yes.
and outside E, inside A and outside, inside, so it's like if you compute the measure, mu star measure of E and abstract E, with inside A and outside A, it should give you the whole measure of E. So if this is true for all E, then you call that, okay, this set is good. So it's mu star measure. Are you getting the point? And have we defined this? Have we define this? What's the meaning of sigma finite? Okay. The meaning of sigma finite is this. L is sigma finite. So sigma finite means this. Okay. That if x, okay, x can be written as the union of, so countable union of some subsets of A, some subsets of X, such that length of all these subsets is finite. What does it mean? So it means, so I'm not saying that the length of whole X is finite, but X can be broken into the parts in which each part has
Finite.
length. Pretty simple. So X is not necessarily finite. So one of the trivial example could be R actually. Think about it. Okay, so R doesn't have a finite length, but you can write R as the union, okay, of, say open intervals, such that in which the open interval has a finite length actually, but not necessarily. So this notion of length on R is somehow sigma finite. Are you getting the point? In other words, if your L is good enough, it has this kind of a property, then you can extend this L to what? To whole, to the sigma-algebra generated by A naught. Are you getting the point?
The second property is that length of AI is less than infinity for all I belong to that interval.
What do you mean by?
Sir, you written that length of AI is less than infinity. For all I belong to interval.
I equal to 1 to n. Not interval, but 1 to infinity. It's like, or I belongs to natural numbers. This is what that means. Is it making sense? Okay. So, starting the proof, but this is what the bigger picture is actually. So this is what that we're going to do. Okay? So you quite often have what is a Lebesgue integral, Lebesgue measure. So all of the probability theory, and many of things usually that you do in PDE theory, you do things through this, what do you call, Lebesgue measure. Not necessarily that you always should have Lebesgue measure, but mostly we are concerned with what do you call Lebesgue measure. Now Lebesgue measure is what? Essentially. So I have R, and I can take A naught to be the collection of open intervals actually. And I can show it's a sigma-algebra. Okay? Not sigma-algebra, but an algebra. Alright? And I have a notion of length on that algebra, L, which is pretty much. Then the Carathéodory extension theorem is saying what? That you can construct an outer measure. Okay? You can construct an outer measure onto what? Onto the whole of the power set of R actually. Okay? We're going to show that this outer measure is not really measured because there are some sets which you can't measure through. So there are non-measurable sets as well. Okay, subsets of R which you can't measure through this. Then what you need to do, you need to restrict, okay, this mu star that you have defined through the notion of length, okay, of intervals. and if you restrict it onto suitable sigma-algebra, so the sigma-algebra generated by open intervals, and what is that sigma-algebra generated by open intervals? It's Borel sigma-algebra. So if you restrict this notion of outer measure to the Borel sigma-algebra, then that becomes a measure actually. And that restricted measure, restricted outer measure, is called Lebesgue measure. Okay? So you can do it in R, you can do it in Rn actually. So if you are doing it in R, you call it a one-dimensional Lebesgue measure. If you do it in Rn, you call it a n-dimensional Lebesgue measure. Okay?
It implies every measure is Lebesgue measure.
I'm sorry?
But it implies every measure is Lebesgue measure.
Not every measure is a Lebesgue measure, every measure is an outer measure. Okay? So it's not every, so it's like Lebesgue measure, so whenever you're talking about Lebesgue measure, you're talking about a very concrete set and a very concrete, what do you call sigma-algebra. But when you are talking about, in general, about outer measures and things, then you are talking very abstractly. Okay? So, Lebesgue measure is only related with, R and the subsets of R actually. This is what you have to think about. Okay? After starting it, we'll do it once more next class. Okay? Whenever that would be. And then we can give. But at least you got the bigger picture actually. What is going on, how to construct a Lebesgue measure. Okay? And the last theorem is telling you that this Carathéodory theorem, that how you can take a simple sigma-algebra and a notion of length associated with it, and you can construct an abstract measure actually.
Yes, sir.
Okay? So, see you.